So I can start. So discussion later. Okay, fine. I'm Fabrizio Ferrandi. I'm from Politecnico of Milan. It's a university. This is open source software developed in our university and together with other peoples. So this talk is related to FPGA design. And the idea is actually that FPGA could be very helpful in order to accelerate some specific application, not for general kind of acceleration, but there are a lot of nice story about accelerating critical key application. Here we have a list of possible acceleration. That acceleration range from 2x to sometimes 100x. The nice things about FPGA is that you have acceleration, but I mean you are able even to control the power consumption. So power is not an issue even if you accelerate very evenly. I mean you have sometimes, for example, for Monte Carlo simulation, 800 to the faster simulation and 45 more efficient in terms of energy, and so on and so forth. So this is the first element of the talk. The second element of the talk is related to how to program these kind of things. I mean, it's not easy, and in the past there are several efforts from handmade design. That is something that currently works even now, till some automated kind of things. I mean, in the past and currently we have investigated how to automatically translate, for example, a behavioral specification down to an RTL description. I mean, my limit in these talks will be something that could be synthesized by standard RTL tools like Xilinx IC or Vivado or Quartus Arteria and so on and so forth. So, but even that kind of thing is not easy. So in the past there are several languages that are used as a way to express the behavior. We moved from, in the past, there was some effort in order to synthesize behavioral VHDL down to RTL VHDL, for example. But that kind of things does not work, since actually you are playing the same game of the hardware designer, providing another language or another extension of the language in order to do the same things that a standard designer usually does. So recently, the kind of specification used in order to automate this kind of process have been moved to something of somehow totally different. I mean, instead of using hardware description language, recently we moved to software language. I mean, like C, C++, Java, for example. There are even, for example, around MIT and some company, there is even some effort in order to do high-level synthesis, starting, for example, from hardware-specific language, like maybe could be BlueSpec. So, but anyway, restricting to a description based on software programming language. In this talk, we mainly consider C function. The idea is to generate for each of the function you have in your description a controller and a data path in hardware. So you have the controller, the elaboration unit to describe in RTL at the end of the process. And that description should be a synthesized Verilog or VHDL kind of things. Technology could be, usually these kind of things target ASIC or FPGA, but I mean, I think that recently the FPGA target seems to be a more available solution to this problem. As usual, this kind of thing seems too easy, but actually designing hardware is not very easy. I mean, you need maybe a PhD or somehow a very high skill in order to do that kind of things. Maybe you need such kind of things even for software. But anyway, it seems that exploiting hardware description, software programming language could be a viable solution in order to implement in hardware some key kernels, and actually it should be helpful in terms of increasing the productivity of the designer. And the other kind of things that could be interesting is that actually the idea is to not to actually need all the skills that hardware designer usually need. And you just need to know C, and more or less that's it. It's not true, but anyway, that is the aim. So that is actually a very nice thing, but what happened at the end, so which is the quality of this kind of tools, is getting better. That's something that is getting better as the time passes. Usually it's worse than handmade RTL design, but I mean, I think it's even true in software. If you write assembler code, you usually are able to do better than any kind of C or high language, high level languages for software programming. But that is one side of the problem. The other kind of nice thing is that usually it's better than software programming. So if you have a microprocessor or microcontroller and you compare the results of the A-level synthesis, usually A-level synthesis win. So that is nice, another nice thing of the HLS. First things about these talks is related to GCC. Why GCC could came in this picture? GCC is a compiler. It starts from a C. It has several front end. It supports several languages. When we try to perform this kind of process to automate the translation from an high-level description to RTL design, we discover actually that there are a lot of things in common with compiler infrastructure. So we start to study GCC in 2004. So this kind of project is 10 years old. And we discovered that actually we may exploit more or less the same intermediate representation exploited by GCC. And so we study that kind of representation, and we extract such kind of representation because at that level of GCC, so the intermediate one, the middle one, where actually all the intermediate transformation are performed, we exploit in such intermediate representation, we may actually exploit all the standard optimization techniques performing in a standard compiler like GCC, even at some advanced one in order and that kind of things. So we developed a plugin that extracts such middle intermediate representation and serialize it in a file, and then we build up over this intermediate representation all the things needed in order to optimize and generate the hardware starting from them. I mean, there is function allocation sharing, memory allocation. In hardware, you need to perform some analysis in order to understand the bit size of the wires and stuff like that. Module allocation, register allocation, and that kind of things generate a controller and data path. At the end, we have a single tool, a command line tool that is able to it's able to start from a C description and generate VHDL and or Verilog. This is the list of features. There is support, more or less, ANSI support is more or less complete. Obviously, recursive function is not so easy to support. We support more or less GCC from 4.5 to 4.9. There is a lot of distribution we support from Ubuntu to Fedora. And there is a rich set of components already developed that perform more or less all the basic functionality you may have at lower level internally in GCC, from addition, subtraction, supporting of floating point, whatever you will have in this kind of things. All these kind of things are described in open source with an XML description that could be easily extendable. There is a support for verification, automatic generation of test bench. We exploit two free software projects in order to perform such simulation. In particular, we exploit Icarus Verilog and Verilator. And also, we support some commercial tools like ModelSim, iSim, or XSim from Xilinx. We have a larger regression test, as any compiler should have. This is a large set taken from academic side and even from GCC. Support for synthesis, more or less the list is almost complete in terms of tools supported. And we are even currently considering even some open source project. In particular, there is Yossi's project that could be very nice in order to perform the synthesis more or less till the end. I mean, we missed the last step, I think, but we are not so far in order to be able to program an FPGA. Some case studies. So, 3 examples. Ketchak is a cryptocore. It was the winner of the SHA-free competition performed some time ago. We take the C description and we compare with the VHDL handmade, developed by the winner of the contest. So obviously control the C is more easy than start to write the VHDL. So that kind of things was passed to Bambu, the tool we developed, and we actually are able to obtain better performance losing some area. I mean, if you look to the lookup table, I mean, it's not so comparable in terms of area, but in terms of performance, it's not so bad. The second example is a nice kind of things that one of my students does, is writing some rectangular circle on a VGA screen, just exploiting some C primitive and having integrated that with a standard core. Finally, we have even tried to synthesize and see which kind of C support we are able to have. And we start from an open source project developed at CERN with other partners. This is pretty large kind of project, but that kind of project we was able to synthesize, and we are able to fit that kind of things in a single zinc board. That's it. We are keen to cooperation, integration with other kind of tools, questions, comments, and whatever. It's very difficult to say so many words in 50 minutes. So. No, pointer is not a problem. Sorry. So the question is, one of the problem of synthesis of program of specification based on C or whatever, is that C thinks to have a shared memory there, and so you have pointers, arithmetical pointers, and whatever it is. We actually are able to deal with that kind of things. Since we have a modular allocation, we use what GCC does in order to figure out which is the size of the element and so on and so forth. We have developed some units that are able to support aligned and a non-aligned access to the memory, more or less as a processor does. So there is a bus where we put the address, the memory return the data, and so on and so forth. That kind of things works, and works pretty efficient.
One more? Can you actually generate most constructs in VHDL using the C language, or are there some constructs which are basically impossible to create from C?
So the question is, there is something that maybe I missed. Maybe you could elaborate a little bit more. But the question is related to that there are some inconsistency between the two languages. Of the
Well, the question is actually, if I have a certain design in VHDL, and I would want to try and create a C code which generates that.
Mm-hmm. So the idea is to reverse engineering the VHDL in C, and then actually have something that could be retargeted to any kind of hardware and so on and so forth. I mean, it's a matter of designer fantasy. I mean, I did such kind of things, for example, for floating point cores. So I start sometimes from VHDL description of available of floating point units, and I try to rewrite everything in C. Actually, most of the time you have to deal with bit size, but that kind of things could be controlled in C through masking and saying that that kind of thing is not greater than that, and so on and so forth. Compiler pretty clever in that kind of things, since, for example, GCC 4.9 start to support value range, and so we just have to add bit value analysis, and so on and so forth. So actually, there are things that could be not easily ported to C. I'm thinking maybe to when you have things concurrent and stuff like that. But I mean, it's another option. I mean, if you are hardware design, as I was most of the time, sometimes it's better to start in hardware design. But I'm trying to do that kind of things that is try to involve people that does not have all the skill usually you have another design have in order to build an FPGA. Just exposing to him tool and see. I mean, that kind of things at the beginning is not optimal, but I mean, it's a trade-off.
Okay, just one more, but quick.
So the question is about recursive function. Recursive function, there are solutions about that. Solutions currently are not implemented in the tools. And solutions concern the allocation of a memory, and so you have a stack. And actually, during the synthesis, you try to mimic what a processor does, building the stack and the parameter allocation you usually have with a recursion. It's even true that at least till now, I do not see any embedded things or high-performance things that could not be translated in an iterative way. GCC, for example, have optimization that automatically translate that kind of thing that could be translated from a recursive version to iterative one. For example, factorial could be an example.
Okay, thank you.
Thanks.